Let's talk about vectors. First of all, what is a vector? A vector is a quantity that has both magnitude and direction. Simple way to think about a vector is that the magnitude of the vector describes how much, and the direction describes to where. One example of a vector quantity could be velocity, in which we could describe the velocity of an object in, say, meters per second, in the direction, say, to the northwest. The difference between a vector and a scalar is that a scalar only has magnitude. An example of a scalar would just be speed, in which we might be able to say an object is moving at a certain speed in meters per second, but we wouldn't be able to describe where it's moving. In physics, we generally designate a vector using boldface font. Not sure how bold I can get that, but because oftentimes we use handwriting, we'll describe it using a little arrow over the font, where scalars are just described using normal script. Now, when drawing a vector, this is a vector, not a scalar down here, we use an arrow. Set up a Cartesian coordinate system here, x and y, and say we have a vector. Let's call this vector vector v, and we use a little arrow to designate the fact that it's a vector. And you're drawing a vector, the length of the arrow designates its magnitude, and where the arrow is facing designates its direction. So one way of describing a vector would be to set up an angle. Say we have some angle theta here, and we could describe vector v saying v has some magnitude, let's say, just for the sake of argument, 10 newtons, at some angle, let's just say 30 degrees, above the positive x-axis. Now you might notice when describing this vector, we do not describe where it is in space, and this illustrates a very important property of vectors, that they only have magnitude and direction intrinsically. They do not have a defined location in space. Now, let's talk about a very important concept of vectors. Let me just redraw vector v over here. Have y, x, and vector v. Vectors can be resolved into what are called components. In this case, you'd have the x component and the y component, because we're dealing in 2 dimensions here. So we would say this x component, v sub x, is always parallel to the x-axis, and this y component, v sub y, is always parallel to the y-axis. Now you might be asking, what if we have a vector, let's call this vector b, that itself is parallel to, say, the x-axis in this case. Call this vector b. In this case, vector b certainly does have a y component, but the y component is equal to 0, so generally we do not write the y component. This vector can be fully described in terms of its x component, b sub x. So when describing vectors in terms of components, you can write, let's use vector v as an example. Vector v is equal to the sum of its components. Now, because this is vector addition, not scalar addition, we can't simply add these two components together because they're projected in different dimensions. This is the y dimension, this is the x dimension. Therefore, we introduce a property that I like to know as I hat, j hat, k hat, I hat, little hat on top of the I, j hat, k hat. And the I hat represents the x direction. So in this case, we would say v is equal to v sub x I hat plus v sub y j hat plus v sub z k hat. Now, because we drew this vector in only two dimensions, v sub z k hat actually just goes to 0. So we're left with just v sub x I hat plus v sub y j hat. And because they have different differentiators after them, you cannot simply add v sub x and v sub y together. So I hat, j hat, k hat is a good way of reminding yourself of that property of vectors. You can't add them on different dimensions. And while we're on the topic of adding vectors, let's discuss that now. So in terms of adding vectors, there are a couple ways of doing this. We'll discuss two. The first of which is known as the tip-to-tail method. Say that we have two vectors. We'll just call them vector A and vector B. And to add them, all you have to do is place the tip of one vector at the tail of the next vector. It doesn't matter what order you do this in, I'll demonstrate. So say we have some vector A, and we place the tail of another vector B at the tip of the first vector A. Now all you have to do is draw what is called the resultant vector from the tail of the first vector to the tip of the final vector, and we'll just call this vector R. Now, as I said before, you can do this in any order you like. I'll just demonstrate this real fast. So we'll draw vector B here. Then we'll put vector A at the tip of vector B. And we'll draw resultant vector R. As you might notice, we're going to get the exact same answer for vector R as before. So another way of looking at vectors is to do the resolution into components like we talked about earlier, but to do it for each vector. So we'll have the same example down here. Let's start with vector A. Perhaps we'll draw this one slightly bigger. So vector A we can resolve into components. So we have, as you saw before, A sub x here, and then parallel to the x-axis this time, A sub y here. And normally when we resolve vectors and components, we draw a backwards S through the vector to remind ourselves that we resolved into components. So now we can draw vector B and resolve this into components as well. Once again, parallel to the y-axis. It doesn't have to be on the y-axis, it has to be parallel to the y-axis. We have B sub y, and parallel to the x-axis, B sub x. Let me just, this is vector B. So now, say we want to add vector A and vector B. So we'll do vector A plus vector B. To do this, we just simply have to add their components. And we have to remember to use the I hat, j hat, k hat nomenclature that we introduced earlier. So we'll say a sub x I hat plus b sub x also I hat because they're on the same x dimension. Then we have b sub x j hat plus b sub x j hat plus a sub, this should be sub y, I'm sorry, b sub y j hat plus a sub y j hat. And that can simply reduce into a sub x plus b sub x I hat plus b sub y plus a sub y j hat. And if you'll notice, it doesn't matter what order we add these in because addition is communicative. So resolution into vectors is probably one of the most powerful, into components, I'm sorry, is probably one of the most powerful things you can do when working with vectors.